Why does one mass move more than all others, even though all springs are identical? The answer is hidden in the eigenvalue problem, and once you see it, you can read mold shapes like an engineer. In this lecture, we focus on interpretation. The goal is to understand why modes look the way they do, and how the specific entries of the mass matrix M and the stiffness matrix K shape the dynamic behavior of a system. We again consider a constrained horizontal 4-mass oscillator with the displacement vector x and the matrices M and K as derived before. What we will now do is varying some of the system parameters and observe how the motor behavior changes. No mathematics, just physical interpretation. We start with a fully symmetric reference system. All masses are equal, and all springs have identical stiffness. If you look at the mass matrix M, this symmetry appears as equal diagonal entries and 0 off-diagonal terms. No degree of freedom carries more inertia than another. Likewise, the stiffness matrix K shows a regular tri-diagonal structure with identical coupling terms between neighboring degrees of freedom. This symmetry has a direct consequence for the mode shapes. In the visualization, no mass is preferred. Motion is distributed smoothly, and amplitudes are comparable across the system. What you see in geometrically is a direct reflection of the fact that mathematically every row and column of M and K plays an equivalent role. Lower modes show smooth deformation patterns where all masses move in the same general direction. In matrix terms, this means that the stiffness couplings do not penalize relative motion strongly at low frequencies. Higher modes introduce sign changes and internal deformation, but still remain spatially balanced because no entry in M or K breaks the symmetry. This reference case is crucial. It establishes a baseline where the mode shapes are governed purely by connectivity, not by dominance of mass or stiffness. Every deviation we introduce next can be interpreted as a deliberate modification of specific matrix entries. So now we modify only the mass distribution while keeping the stiffness matrix unchanged. The mass matrix M, one diagonal entry is now 3 times larger than the others. This single move already changes the dynamic behavior significantly. You immediately see that the corresponding mass oscillates with the larger amplitude in the first mode. This is not because the spring forces acting on it are larger. They are identical, but because its inertia dominates the kinetic energy balance. From the eigenvalue problem, a larger diagonal entry in M means that for a given stiffness, acceleration at this degree of freedom becomes more, let's say, expensive in terms of frequency. As a result, eigenfrequencies decrease and mode shapes for higher frequencies adapt by concentrating motion where inertia is lower. Visually, this appears as a mode shape where one component, phi, is clearly dominant. Mathematically, this dominance corresponds to a system minimizing elastic energy while accommodating the large inertial contribution encoded in M. Engineers who master the eigenvalue problem understand where a structure will fail before it is built. Learn to apply these methods like a professional on interesting real-world exercises. Link with free chapters is in the description. Next, we keep all masses equal and increase the stiffness of one spring significantly. In the stiffness matrix K, this modification appears as larger diagonal terms for the connected degrees of freedom and a stronger negative off-diagonal coupling between them. In the visualization, this tip spring hardly deforms. Instead, motion is redirected to other parts of the system. This behavior is a direct consequence of how the stiffness matrix K penalizes relative displacements. Large stiffness entries increase the energetic costs of deformation across that connection. In matrix terms, large coupling values suppress the relative displacement between the two degrees of freedom. As a result, mode shapes bend around the stiff region and concentrate deformation there where stiffness is lower. Geometrically, you see small amplitudes near the stiff spring and larger amplitudes elsewhere. With a strongly non-uniform stiffness distribution, we now observe a clear separation between global and local modes. In the stiffness matrix K, alternating large and small entries introduce preferred deformation paths. In global modes, several degrees of freedom move with comparable amplitudes. This occurs when the stiffness couplings distribute deformation across the structure, resulting in similar eigenvector components. Local modes, in contrast, are dominated by 1 or 2 degrees of freedom. In the visualization, this appears as large amplitudes concentrated in a small region. In matrix terms, these modes exploit weak stiffness connections while avoiding stiff ones. A practical indicator is the curvature of the mold shape. High curvature and abrupt sign changes usually point to strong stiffness contrast encoded in K. Now we'll consider the spacing of eigenfrequencies. With equal masses, frequencies tend to cluster. When masses differ strongly, the spectrum spreads. This behavior can be understood directly from the ratio of stiffness to mass. Light masses connected by moderate stiffness leads to high frequencies, while heavy masses supported by the same stiffness generates low frequencies. An effective qualitative estimation strategy is to ask which mass dominates this mode, or through which stiffness path is it constrained. Visually, the mass with the largest amplitudes usually determines the frequency level of that mode. Mathematically, this dominance reflects the balance between corresponding diagonal entries in M and K. Finally, we will observe the nodal points in the mode shapes. This means locations where the displacement is zero. These nodes are not explicit entries in M or K, but they emerge from the interaction of mass and stiffness encoded in both matrices. Nodes occur where stiffness constraints and inertia balance, such that the motion cancels. In the eigenvector, this appears as components that are numerically close to zero. From a practical standpoint, this has direct consequences. Exciting the system at the nodal point of a mode will hardly activate that mode. Likewise, placing a sensor at the nodal position provides little information about that mode. With all that knowledge gained in the last lectures, we are now ready to apply these methods to real-world tasks in the exercises. Have fun with it.